Welcome to Hot Chips 31. Session 1, General Purpose Compute.
Good morning, everyone. Welcome to Hot Chips 31. My name is John Davis. I'm the General Chair. We're excited to have you here at Stanford. I'm from Barcelona Supercomputing in Spain. This is a conference that is sponsored by IEEE. I'm going to go through a few things to help you through the day, and hopefully you enjoy our return back to Stanford. So if you didn't know, you're at Stanford. Hopefully you know that. We have record registration numbers this year, and we continue to grow, so this is fantastic. What I want to do is also go through, and there's a bunch of people I'd like to thank, at least let them know we appreciate what they're doing for us. We have a bunch of different sponsors this year. It's a record sponsorship year. Intel is sponsoring the food for the conference for Monday and Tuesday. I have some other information about them on another event that they're doing. Including Intel, we have 6 platinum or better sponsors. On the next level lower, we have 7 gold sponsors and 10 silver sponsors. A lot of these sponsors are out here in the patio area, so go talk to them and see what they're doing. Fundamentally, what that means to you is we're able to keep the registration costs for the conference low. So when you see a sponsor, please thank them. If you have registered for the Intel Hot Wings event, they'll be on interstitial slides and in your bags information of where to go for the free shuttle. It's in the Alumni Center. You'll pass that as you go back to parking. They'll bring you back to Galvez parking after that. So enjoy that as well. If you didn't know where parking was, it's kind of behind us. You need a parking pass. The only place that you can park is Galvez or the Eucalyptus Grove. So please do not park anywhere else because you will get ticketed from that purpose. If you need parking passes, the registration desk has it. And there's also parking attendants. So please park in the right place. Food is in a variety of places. We'll be doing breaks and breakfasts over here on stage left in the patio. We have lunch in Dorman Grove, as you can see in the picture. It's just right out front here. Food is served there, and then overflow seating is in the Oval Ear on the east side. So if you can't find seating there, just keep on walking, and volunteers will show you where that is. The reception as well will be tonight at the end of the day in Dorman Grove as well. So hopefully that's pretty straightforward. We will be providing the presentation online. There's the website and the password for it. There'll be information around the room with that. If you need to figure out how to get on Wi-Fi, if you look at the back of your badges, the information is there. There's also posted signs, so please use at your discretion. There's both the Stanford Network, which goes through this process, and if you have issues, you can try the Stanford Visitor Network, which is a click-through. So when we look at Hot Chips as a conference, it's a volunteer-run conference. There's a volunteer steering committee, a volunteer organizing committee, a program committee, as well as the volunteers here to help you through your day. Please reach out and thank them. They have black shirts with the Hot Chips logo on it, so you can tell them who they are. There's lost and found at the registration desk. If you've lost something or found something, please go there and they'll help you out. So just for some context, I wanted just to go through kind of Hot Chips over history. It was started at Stanford, first at Kresge, and then moved to Memorial Auditorium. The last time we were here was Hot Chips 25, so it's been a little bit of time. We spent a bunch of time at De Anza College and Flint Center. Flint Center is no more. So when you look at what we're doing back here at Stanford, please excuse the dust from the getting back to the Stanford place, as well as the construction that's around here. But hopefully you enjoy the beautiful setting. There is power throughout the auditorium, both downstairs and upstairs, so that's a good thing from that perspective. Just to give us context, when you look at Hot Chips, the first one, there are things that we no longer talk about. So that's kind of fun. And then the actual sessions for this one, so just as a juxtaposition. And then when we look at this in terms of word clouds, what I wanted to do is see speaker affiliations or companies that were participating, as well as their titles. So as you look over these decades, we see obviously some stalwart companies that you know and love, as well as some that are no longer in existence, from Hot Chips 1 to Hot Chips 2, Hot Chips 10, Hot Chips 20, as well as today. So it's interesting to see that evolution over the 30 plus years. On the presentation side, there's a lot of old terms that some of you may not be familiar with. Some of you probably are. And they evolve over time as you go every decade. The most interesting thing about this is that the titles are getting longer. Not sure the content is getting better. But that's the question that you guys get to decide. I'm super excited about the program. There is so much interesting content here, both from established companies as well as new companies, so enjoy the show. I'm going to pass this on to my program co-chairs, and they're going to go through some of the details there. They are Christos and Ian, in case you can't read the slide.
Good morning, everybody. Welcome to Hot Chips 31. It's a really great pleasure to have you here. I'm Christos Kozirakis and Ian Brad, who is supposed to be somewhere here. We had the honor to co-chair this year's program committee. And these are the gentlemen and ladies that were on the program committee, and they did all the hard work of soliciting, evaluating talks, and making sure that the talks meet the quality of Hot Chips. We work really hard to make sure that we get solid technical talks and not marketing pitches. All right, a few quick numbers. This was just an amazing year reflecting the really great activity in our domain. We got about 88 submissions. We selected 26 talks. Honestly, we could have selected the next 15, and they would be also great talks. We had the weird situation where we rejected talks that would be begging for other years, and it's a phenomenal year. So the program is pretty strong. We've got a really great set of announcements of ML-related chips, and of course the latest CPUs, GPUs, FPGAs, and so on. But we also have talks on a number of technologies that are pretty critical in building systems: memory chips, interconnects, and packaging design, chips for embedded and automotive applications, and of course security. As we've done the last few years, we also have a few posters that will be displayed on the side of the building during the break. So this could be a really great thing to do during the breaks as you catch up with your industry friends. If you were not here yesterday, we had two great tutorials, one in the morning about how AWS, Microsoft, and Google use acceleration in the cloud for anything from their own basic infrastructure to machine learning. And we had a long tutorial about RISC-V and its ecosystem in the afternoon. So if you're not here, you can look at the material offline. I highly recommend this. We're really excited about the two keynotes. Today we have Dr. Lisa Su from AMD, the CEO of AMD. Who's going to tell us about her view for the future of the industry. And then tomorrow we're going to have Dr. Philip Wong, who is a VP of Research at TSMC and a colleague of mine at Stanford. And he's going to tell us about where is technology moving to. And I think these two talks are really going to be quite exciting. So if you are new to Hot Chips, what we've done the last few years is that we make the talks available to you online. There's the link again, in case you didn't see it, and the password. Some of the talks I will be released at the morning of the talk. Some of them we're going to release them literally at the time of the talk to give a chance to the comers to make their corresponding announcements. We're videotaping everything, and at some point we're going to make all the videos available. And of course, we eventually make everything freely available online within a couple of months. If you go to the Hot Chips site, you're going to find all the material from the very first Hot Chips available, including the videos that we've got from the last few conferences. All right, with that, welcome again to Hot Chips. We think we have a great program. I hope you will enjoy it, and we're looking forward to any feedback you have. Thank you.
Morning. Pradeep Dubey from Intel Labs. We are starting our morning session with some exciting processor talks. One nice trivia to note, this is, of course, Bay Area, but you'll realize that the first three talks have their roots in Austin. This is Austin asserting itself on Bay Area. Okay. And the very first talk is from AMD, and we have David Suggs and Dan Bouvier, who will be giving the talk jointly. David is an AMD fellow and chief architect for the Zen 2 architectures, Zen 2 core. Previously, he was also the architect for opcache and instruction decoder for ZenCore. For the past 26 years, he has worked on architecture projects, pretty much all sorts of projects related to CPU core, North Bridge, South Bridge, voice telephony, PC sound cards, DSPs, just name it. He has a master's from UT Austin and an MBA degree. And Dan Bouvier, he's a corporate vice president and chief architect for AMD's Ryzen products. He has defined 5 generations of AMD notebook and desktop processors during his 32 years career. Dan has focused on high-performance processors, SoCs. Prior to joining AMD, he was CTO for Applied Microcircuit at Applied Microcircuits, and also director of advanced processor architecture for PowerPC at Freescale Motorola. So now, without further ado, let me welcome David and then Dan.
Thank you. It's great to be here. So processor development is a collaborative effort, and Zen 2 is no exception. We're so honored to be here today. Thank you, Dan. So honored to be here today representing the Zen 2 team. So this presentation will be in 2 parts. First, I'll talk about the ZenCore itself, and then Dan will present the solutions that we've built around the ZenCore, including our server and our desktop. The path to Zen 2. So we had some fairly challenging goals when we started. We wanted to meet multiple markets from server to mobile, everything in between, some things not in between. We wanted a few things like ultimate performance and ultimate energy efficiency while we got that performance. One of the key things that helped enable this was our 7-nanometer technology, which enabled scaling in terms of core count, as well as we were scaling to manage power. On the platform side, Dan's going to spend a good bit of time talking about chiplets and how chiplets help us deliver the right technology into the right markets and the right needs. We were able to upgrade our I/O to meet increasing system demands, and we were also able to maintain compatibility across generations in the socket. So the Zen 2 top-level microarchitecture. Microarchitecture is my favorite part. You may look at this and you note that it looks familiar if you're used to seeing Zen. And there's nothing better to start with than the bones of a good microprocessor, which is what Zen was. So before we even started Zen 2, before it was really even kicked off, we had already begun working on a new branch predictor called Tage. And Tage has a lot of degrees of freedom. It has sizing of individual tables, number of tables, length of history that indexes into the various tables. And so we'd spent months tuning Tage before we started Zen, so we got a good head start there. And there were a number of other features that were kind of key in Zen 2 that I'll list here. We doubled the size of the opcache, and that's something that was very much a challenge to fit into the same pipeline that we had on Zen. That's something that even halfway through the program, we were still struggling to meet timing, and people were still uncertain whether we could build that feature. Another thing that was interesting is on Zen, we had the capability of 2 loads in 1 store. We have that in Zen 2 as well, but we've added a third address generation unit to better balance that out. We were able to double the FP data path width, and again here, the 7-nanometer technology was a key to being able to do that. Being able to do that at the same time as scaling the number of cores and doing it in a reasonable power envelope. We doubled our L3 capacity, which is something that helps in a wide variety of workloads, including, but not limited to gaming. So when we started Zen 2, our initial goal was we want to get 6 to 9% IPC uplift over Zen. But this team is not satisfied with that goal. In fact, it almost doesn't matter what goal you give the team. They're going to be hungry for more. And in the end, we ended up with 15% IPC improvement over Zen 2. So Zen 2 has some major efficiency improvements. We measured in silicon from Zen to Zen 2 in integer workloads, double the number of instructions per incremental unit of energy. And you might look at that and say, well, 7 nanometer is a big part of that, and certainly it is, but it's not the only component. There was a huge amount of work done on design as well. So we had, I'm putting a 1.15 factor here for IPC. As you probably know, as you increase IPC, generally speaking, energy goes up. But our goal was to maintain energy neutral microarchitecturally as we increased IPC, and even do a little bit better than that. But remember, since our IPC goal was more modest in the beginning, as time went by, this energy goal got to be more and more aggressive. And again, the team wasn't sure if that was possible. But in addition to neutralizing that IPC energy, we also got another 1.17 efficiency multiplier from design. And some of the things that made that possible, we improved our branch predictor accuracy, which means we get IPC and we spend less time wasted on useless instructions. Higher op cache hit rate lets us bypass decode and get better power, better efficiency. The integer scheduler is an area that we frequently look at as a high power area. And so we came up with some novel algorithms there that let us save energy with no cost in IPC. As well as we continued our usual cast of clock and data gating improvements, improving our methodology from what was already very good in Zen. Zen 2 is designed for security. We have our standard Spectre v2 and v4 mitigations in Zen 2. We've more closely implemented those in hardware, as well as added some acceleration of those functions. And the Zen 2 microarchitecture has some good design choices that I think help us in the security field. We do hardware permission checks, and we do them up front prior to consuming data, even speculatively. So that helps us avoid a whole class of possible security issues. On the virtualization front, Zen had SEV, which is secure encrypted virtualization. It lets the guest memory be encrypted with its own key per guest. The ES feature that we've added in Zen 2 lets us additionally encrypt the guest register state. We've added a lot more keys, so we now support up to 509 encrypted guests. And we've added a couple of features that help the hypervisor provide better security for the guests. VTE lets the hypervisor specify that guests are to be encrypted. It can even be used in the presence of guests that aren't even aware of that as a feature. GMET allows hypervisor to trap guest execution of pages so that it can do integrity checking on those pages and, again, provide better security for the guest. Other ISA features that we added X2 APIC, which was necessary for us to scale core count as much as we wanted to. QoS is something that's important in an environment where you have multiple virtual machines, and those machines may be noisy neighbors with one another. So we have quality of service monitoring for L3 cache occupancy and for memory bandwidth, and we have enforcement of caps of those same quantities. We have a couple of features that are targeted primarily at non-volatile memory. And the idea here is to write back dirty data and keep that data resident in the caches so that you can get the performance of re-referencing the clean data. So CLWB is one of those functions that's done on a cache line granularity. You can specify writing back a cache line. Write back non-validate is more of a entire cache granularity function for that. So we have a new instruction called read PRU that allows us to read some timers at the user level. It's currently mperf and aperf, but it's designed to be extensible, so we could add to this functionality of this instruction in the future. So now I'll dive into the individual blocks in the microarchitecture. So starting with the front end, as I mentioned, we have Tage as our new L2 predictor. We've also nearly doubled all the sizes of our 3 levels of BTB, L0 through L2. We've also doubled the size of our indirect targets, and all these things together net us our targeted 30% lower mispredict rate. We optimize the L1 iCache. What does optimize mean? In this case, it means optimized for area. We actually halved the capacity of the iCache, upped its associativity. And why do we do that? As you may know, if you're into cache design, 32K 8-way is sort of a magic design point where you can avoid having to index the cache with translated bits. So that does help timing. It tends to help power some too. The main reason we did this is to make room for the op cache. We wanted to double the op cache. I call it op cache instead of micro op cache because it really doesn't store micro ops. It stores more like decoded instructions. In this case, it stores fuse instructions, which means you can have up to 2 instructions in a particular op entry of the op cache. So we don't cover additional cases of fusion from an ISA point of view, but we do cover microarchitecturally more cases of fusion, so we're able to get more benefit there from fusion. We also are able to do better effective throughput, which means that the op cache is able to deliver more ops in the presence of branch corrections. Inter-execution. So one of the themes here is wider issue and deeper window. As I mentioned, we added a third address generation unit. In terms of deeper window, we made our scheduler bigger. The ALU scheduler was distributed into 4 ways previously, and that's the same today in Zen 2. We've just increased the size of the queues. And the AGU scheduler didn't actually increase its raw capacity, but it did become unified. And as it becomes unified, that tends to make the effective capacity bigger because there are no limitations on which queue particular ops can go in. Additionally, we do realize another performance benefit here because of being able to do better age-ordered picks out of the unified queue. More window size by increasing the size of the register file and the reorder buffer. We've also added logic to improve fairness for the schedulers. And the idea here is you may have one thread that's inherently a low-performing thread. For example, it has a lot of L3 misses. And another thread that could be, it has a potential to be a high-performing thread, but it's not able to perform nearly up to its potential because this low-performing thread is using a lot of resources. So we have the ability to prioritize the high-performing thread so that it can achieve closer to its true potential without really penalizing the other thread. On the floating point side, one thing to note is that our ISA is not different than from Zen to Zen 2. Zen already supported AVX 256, so 256-bit vectors. Zen 2 also supports this, but what's different is that whereas Zen supported this as double pumped 128-bit data path, Zen 2 supports this natively as 256-bit data path. And with a big data path width comes a lot more responsibility in terms of electrical design current management, so we've added capability there for that. Our register file is the same number of entries, but because it's double the width, if you're using 256-bit vectors, you actually get double the number of values, say double precision floating point values. And we've improved the multiply latency as well. So load store and L1 data cache. Another component of bigger window is bigger store queue. We also made the L2 DTLB bigger, and it now natively supports 1 gig pages. It supports them as smashed into 2 meg pages in the TLB. It's lower latency. We added in the L1 data cache, it's the same size and associativity as it was in Zen, but now because it has double the width of reads and double the width of writes, and because we have the third AGen, now we actually have triple the load plus store bandwidth as what Zen had, up to 96 bytes a clock now. We've also improved write combining buffer performance, keeping write combining buffers open as long as possible so we can support more parallel streams. And as we scale the number of cores out, depending on workload, fabric or memory bandwidth can become limiters, and so we've really put some good focus there on improving prefetch throttling there. So now I'd like to introduce Dan, and Dan's going to take over and talk about the solutions that we've built around the Zen 2 core.
Okay, thanks, David. So I'm going to talk to you about our first round of products, and this is our 3rd generation, hard to believe already, 3rd generation of Ryzen. Code name for this was Matisse, and our 2nd generation of the EPYC server device, code name Rome. And so we'll start out with how we compose the core complexes for these processors. So first of all, up in the corner there, you can see the core complex, or the core itself that David's been talking about. We took that, built a similar complex, or CCX, to what we did in the previous generation, where we have an L2 associated with each core dedicated, and then we have a combined 16-way set associative L3. This generation, we doubled the size of that L3, and that, I'll show you some of the results in a minute on how that helped with our miss penalty. We maintained a very similar latency across these caches, even though growing them, and the technology gave us some of that ability. This round, what we did is took 2 of those core complexes, and we put them into a compute core device or die, CCD, and you can see that in the lower corner. And we attached then to that an Infinity Fabric link or an Infinity link. And I'll show you why we did that in the next couple slides. So as we started to build the SoCs and we went into this, we said we want to do a whole family of products from a very, very high-end, world-class server product, eventually, down into mobile. And so, and as we looked at the first two products, the server and the desktop product, we wanted to get those to market fast. We were looking early on at 7 nanometer technology and realized that there is a cost challenge of per millimeter squared. And so we wanted to make sure that what we built took effective use from both a performance and a cost standpoint. Also, we saw early on that the moving or migration of the analog components really didn't scale very well into 7 nanometer, and said, okay, maybe we can take advantage of 12 nanometer for that. And then by doing partitioning, we said, hey, we could very quickly cover a wide range of products. And so really that's the results. So as you see here, this is the composition using chiplets that we came out with. So we started with the building block of that CCD that I mentioned earlier in 7 nanometer. Each one of those is 3.8 billion transistors, about 75 millimeters squared, 74. And then we attach those to an I/O die, and we built two flavors of that for this generation, a server I/O die and a client desktop I/O die. And as you can see, it's about 8 billion, just over 8 billion transistors in that server I/O die. The client I/O die is about a quarter. As we were working through this, there was a recognition that a lot of the I/O functions that were on this I/O die lent themselves also to system expansion or a chipset. And so we took advantage of that. And you can see in the lower right corner, we took that die, placed it into a BGA, and we could put that out on the motherboard, just had to add a PCI switch function, and it became a chipset. So we got 3 for 1 out of all of these, or 2 for 1 out of that I/O die. So let's talk about the desktop part first. So Matisse is comprised of that client I/O die plus 2 CCDs. So that makes for a 16-core, up to a 16-core. We have today a 12-core in market, and then shortly we'll have a 16-core device with our 3950X that's coming soon. And so on this device drops into our AM4 infrastructure. We kept the same power envelope, and I'll show you why this is important as we go forward. The other thing that we upgraded was the I/O subsystem. We moved into Generation 4, or PCI Gen 4, doubling that PCI bandwidth to the peripherals, graphics cards, storage, and so on. We did a cleanup and did some more engineering around the memory controller, supporting up to 3200 DDR4, but we also set the chip up so that we can overclock, which a lot of people like to do, and you probably see in the reviews that this device is overclocking quite well on the memory interface. And again, I mentioned the AM4 socket compatibility. By the way, this is pretty much almost unprecedented now how many generations will have run that socket and still maintaining compatibility. So here's some of the results of having, first of all those cores in that same 105-watt power envelope that we've been running now for a couple of generations. You can see Cinebench just got a big kick, 80% uplift in that same power envelope, and Pavre also close to 70%. And then with creator applications like Adobe and Handbrake, those cores really do play an advantage to speeding up that type of performance. Now the thing is that a lot of people like to buy these for gaming, and so they ask, well, how is this going to do gaming? And we did make some improvements. Now, most of the games today are not exploiting the large number of cores, so we had to focus other areas, and that was on memory latency and so on. And so we did get an improvement there with the memory latency improvements, or actually say the missed penalty improvements with that big cache, and that helped a lot with several of these titles. You can see common game like League of Legends, we see a 30% uplift over our previous generation 2700X device. So good gaming uplift, and really very competitive now, and very useful rig for building gaming boxes. And then if we take advantage of that PCI, again, kind of shift back to that creator or content creation market, and you can see some of the benefits here that having Zen 2 and having the high core count, but then having that Gen 4 PCI Express link balances out that system with NVMe drives. And so, we're seeing upwards to a 51% improvement in NVMe write with like a crystal diskmark sequential test. And again, that will show up in real-world content creation applications like DaVinci Resolve. So we're very happy with the performance around Gen 4, especially in drives, and soon we'll start seeing also graphics cards exploiting that performance as well. So let's shift gears now to the big guy. This is Rome. And again, built on the same chassis, the same building blocks, but much larger. And so what is shown here is very similar to the way that the product actually is assembled, if you look at the die floor plan. And so we have up to 8 chiplets, 4 on each side of the package of the I/O die. And then we bring PCI connectivity down the top and bottom, and then the DDR interfaces out the side. This has 8 memory channels, and so to pause here, if you look at the top, this was 1,000 millimeters squared of silicon. Now the interesting point that one of our server guys pointed out to me is this is larger than you could put on a reticle. And so if you're facing that to subdivide, we chose this path, and the main reason was by having a common centralized I/O die with all the memory channels, we get uniform memory latency. And as a matter of fact, through tuning and so on, we only took about a 4 nanosecond penalty going across this die compared to the previous generation across just with only 8 cores where we had cores and I/O all together on the same die. So the trade-off turned out to be quite good. So this improves the NUMA performance and so on. And then we have class-leading I/O with 128 lanes of PCI Express Gen 4 and maintaining that platform compatibility again with our SP3 socket from the previous EPIC 1. So we can take 2 of those ROMs, because one wouldn't be, 64 cores is not enough. You really need 128 cores and 256 threads to really realize the TCO, or the total cost of ownership, in a server data center. And so here what I show is that we have that infinity link now between the 2 sockets to form that large system. To show the real amazing performance out of this, I grabbed the Spec 17 and contrast this to Cascade Lake that's in market right now in a very similar power envelope. And you can see the amazing advantage then of that 7 nanometer core, the power efficiency, the IPC, and the overall efficiency that David talked about earlier, topping out at about 750 Spec rate there. And so again, you can imagine that advantage of the to the data center of having so much horsepower in such a small footprint and cost. We talked about floating point earlier, so now I take that and apply that 2P and compare again to that Cascade Lake on the server side in HPC type applications, and taking advantage of floating point and integer in those types of applications. And again, you can see across a variety of applications here the significant throughput advantage of Rome in HPC real world applications, as much as close to 100% advantage in performance. So very, very compelling. So with that, we've shown you the ZenCore, Zen 2 core, and that it delivered on IPC well beyond what we had originally set out to with that 15%, but also then the 2x instruction per unit energy advantage. The chiplet deployment that we showed played out very well for us, enabling very efficient targeting of the technology between 7 nanometer with our cores and taking advantage of 12 nanometer for the I/O subsystem and memory subsystem. And it also then allowed us much faster deployment of essentially 3 devices within a couple of months here. We've been in mass production now for millions of units now for a few months with the Matisse device, and then we announced just over a week ago the Epic 2, and that it's in production as well. So to get that to market is quite a feat, and just shows the advantage of chiplet. This resulted in world-class, with Matisse, highest multi-thread performance in the desktop segment in the class, and then unprecedented leadership with over 80 world records now on the Epic 2 device Rome. And so with that, I thank you for your attention, and I think we'll take some questions.
Questions? Please introduce yourself, and then you can go ahead.
Hi, Kevin Crewell, Curious Research. So for the CCDs, you chose 8 cores per chiplet, but you used 2 of them stacked next to each other. Why not build one chiplet with 16 cores?
Yeah, that's a great question. As we looked at that trade-off, what we saw in this generation was that going larger with a monolithic L3 was going to hurt the trade-off in latency and bandwidth. And through the analysis in that assembly, we found that our sweet spot was to keep it at 4 per 16 meg. So we doubled that L3. To double again was going to create challenges in the crossbar, the cross-connect link that we have for the cores, and would have caused scale-out challenges and a performance impact. So that just became the cut point.
Thanks.
Hi, Charlie DeMergent from Semi-Accurate. I've seen a bunch of presentations, the desktop and the server brief, and in all of them, the IOD seems to go from 12 to 14, 14 to 12, back and forth. Can you clarify which one it is and why?
Yeah, I think, there has been some confusion. I think it is definitely the devices are in 12 nanometer. The 2 nodes are very similar. We did run silicon in both. We are in production. It's all in 12 at this point. So sorry for the confusion on that.
Bill Rash, Intel. There have been several IPC numbers mentioned for the improvement in Zen and Rome and Matisse. What are the differences between 15 and 25%? What accounts for that?
Well, I could start there, I guess. In terms of the core, we wanted to have a metric that we could measure core performance independent of what type of SoC it was in. And we also wanted to make that metric be consistent from what we did in Zen, where we were comparing the 53% improvement versus the previous generation. So we use Spec Int 1T, and if you look in the end notes, you can see maybe some more details there about what we did exactly. But that was kind of how we wanted to measure the integer performance of the core, and to be consistent with what we did on Zen.
Yeah, I think that.
Could you characterize what outside the core then did to contribute to the rest of the IPC?
Sure, well, it depends on what you count as the core. Sometimes we count it as including the L3 or not including the L3. Certainly in these cases, the L3 doubling was a big component that, like I say, depending on how you measure outside the core. I don't know if you want to have any other comments?
No, I think that gets it. I know that in large scale-out applications, we've got a significant bump because if you look in Rome, with that latency consistency, again on the multi-core type benchmarks, big improvement there. Again, due to uniform latency and not having to take into account such a big NUMA factor. But generally, I think David hit it.
Okay, thank you.
Okay, one last quick question.
Yes, I'd like to ask, having to do with...
Just introduce yourself, please.
Robert Marston. I would like to ask about the fact that the core has now been separated, the core function has been separated from the I/O, and I mean the I/O. Can they be developed independently in terms of, you've got a number of different types of controllers. You use DDR4, DDR5, GDDR6 HBM. Can they be developed like independently now and manufactured independently and employed in that?
Yeah, I mean, that's right. That's the advantage of this partitioning, and not only that, if you think about building a device, there's so many factors, so many disciplines involved and so on. If we take that core function, which is very critical, tuned, and so on for the process, we have that very contained. The die is small, so it yields very well. That helps in cost. Now we move the I/O. Maybe we're not pushing the frequencies on that die as high. That's nice. Different team integrating that, and with a nice defined interface with Infinity Link, we're able to then build something that's very modular and we can sustain for generations. So that's the advantage for sure.
Thank you.
Thank you. Let's thank the speakers.
Thank you.
So our next talk is from ARM, and it's on their Neoverse N1 CPU and SoC. And the speaker is Andrea Pellegrini. He's a senior principal engineer at ARM. He leads their performance and workload team. He got his bachelor's and master's from University of Bologna, Italy, and PhD from University of Michigan, Ann Arbor. Okay, so let's welcome Andrea.
Here I am. Thank you, everybody. It's a huge honor for me to be here as well. And today, I want to walk through the Neoverse N1 line of products and give you a little bit of details, actually, on how we went about designing this new machine that we're very, very excited about. So at ARM, we have a vision that by 2035, 1 trillion devices will be connected through the internet. Neoverse N1 is really our first step to create an infrastructure that can support this kind of traffic from the edge all the way to the cloud. And N1 is really the first step for us in our roadmap. There is a lot of deployments, if you look at actually in the field right now, of Cortex-A72 based systems. N1 is the first design that was actually architected with the cloud server and networking workloads in mind. We do have a very aggressive roadmap in terms of what we want to do to improve on performance as we move from N1 to our next generation Zeus and Poseidon platforms. So we target at least 30% improvement in performance as we move over time. But as you will see today, what we achieved actually with N1 in terms of performance improvement versus Cortex-A72 is actually much, much higher than 30%. And as you know, ARM is not actually a chip company. We don't actually do silicon. We do not sell silicon. What we do, though, is actually create IPs that partners can integrate in larger SoCs. So, of course, we have a core IP. That's our Neoverse N1 CPU that we'll be talking about. But we also have a number of system IPs, such as the coherent mesh network, interrupt controllers, memory management units. We also have power control kits and crypto islands to allow customers to actually perform securely all the crypto functions on chip. That's obviously not enough to create a full SoC. So for some of the IPs that are needed for the rest of the functionalities, such as memory controllers and I/O connectivity, such as PCIe and C6 root ports, we actually do rely on third-party IPs. And there's plenty, actually, of very good IPs in the market to enable partners to put together a fully functional SoC. What we do guarantee as ARM, however, is that systems that are built within our architecture share the same requirements, specifications, and really the same system-level architecture, such that software could run seamlessly, independently on who builds the SoC or who the silicon partner targets in their market. And what I wanted to start with is actually to look at what silicon partners could do with a Neoverse N1 platform system. And I want to start actually with a fairly large design. What I'm showing here is a 6x6 matrix of Neoverse N1 cores. In this particular design, there are 64, but we can go up to 128 cores on a single coherent mesh. The mesh actually can scale all the way up to 8 by 8. And in this particular design point, we decided actually to focus on 128 PCIe Gen 4 lanes. 8 memory controllers of DDR4 are present to support bandwidth to all the cores in the system. And there's also actually some C6 connectivity for coherent acceleration of die. In order to accelerate the time to market for our customers, ARM provides PPA data for 7-nanometer implementations for reference designs like this, as well as actually configuration parameters for all the APs, such that they can well interact with each other, and also actually provide guidelines on how to program the different APs. And really, one of the big capabilities we bring to the table is really good general purpose compute. I'm going to talk you through some of that in a little bit. But we also offer the capability for customers to plug in accelerators into these dies. Could be either actually by having custom accelerators directly connected into the coherent mesh, or by using C6 PCIe or PCIe endpoints. And let's look a little bit actually into each of these tiles of this reference design. These tiles can scale up from very small systems, just a couple of tiles, as I said, all the way up to 64 tiles. So it can really range actually. You can have a really good range of products you can deploy with ROPs. And the latency and the bandwidth that you can achieve with this mesh is quite impressive. It's only a single hop per cross point, and is at 2.2 gigahertz. The max bandwidth per link per direction is 256 bits, again at 2.2 gigahertz. And the system level cache plugs directly into the mesh. That's shared obviously among all the cores, but accelerators and IO devices can also actually place the data directly from peripherals directly into the L3. When we look at the details of the core, we see actually a design that was really optimized for every workload that really matters for the cloud and for networking, and really optimized for sustained performance. For instance, for the first time at ARM, we have a fully hardware coherent instruction cache. We have a very large L2 available for partners, all the way up to 1 megabyte per L2 per core. And we optimize the design such that cores can directly be connected to the coherent mesh for low latency. The cores are fully ARM v8.2 compliant. They have all the Rust capabilities you would expect in a system that goes into the market, and has specific infrastructure architecture features, such as support for atomic instructions, for persistent memory, and for instance, dot product multipliers. At ARM, actually, we really focus on having very high efficient cores, and N1 really goes above and beyond what we did in the past. Cortex-A72 was already a very efficient core. We actually improved the performance efficiency for this core compared to A72 by 30%. And let's look a little bit, actually, about what we can achieve with a core like this. Our projections that are actually supported from silicon data that we measured is that a single core, including the L2 cache, consumes between 1 and 1.8 watts. This is actually running a very heavy integer workload. And this range actually depends on what clock frequency you run it, either 2.6 or 3.1 gigahertz. We're also extremely area efficient. So the area footprint that we estimated for our core is between 1.15 square millimeters and 1.4 square millimeters, depending on whether you have a half a meg L2 cache or a 1 meg L2 cache. And when we aggregate 64 of these cores on a single SoC, we estimated that we can achieve a Spec in rate 2017 score of roughly 190. And this is actually within a power envelope for a whole SoC of about 105 watts. So we're very, very pleased actually with these numbers and excited to see what partners can do with a machine like this. So Let's dig a little bit more, actually, about Spec CPUs 2017. And there are a number of changes that were made, actually, in the core as well as in the SoC architecture to achieve these results. What we do from early silicon data is that systems based on Neoverse N1 have very competitive performance compared to what people expect for instance, machines that are deployed in the cloud. So we're very looking forward to see silicon in the field. Some of the other improvements that got us to this point are, as I said, larger caches. The front end for the machine is much wider, it's now 4 wide. And there are a number of load store queue optimizations and optimizations, the prefetchers that also help with this performance uplift. We also doubled the floating point throughput on N1 versus Cortex-A72. If we look at the overall performance improvements and speed up of N1 versus A72, we measure on silicon up to 85% improvement for ISO configuration between these two platforms. So much, much higher, actually, than the 30% that we were targeting. One note, as I go through some of these numbers, again, we don't do silicon. There are many, many opportunities for silicon partners to improve above these figures. There's a lot of back-end work that can go to achieve more efficient and higher frequency cores, as well as a number of architectural knobs that people can play with to improve performance and PPA. Additionally, these systems are starting to come online, but as silicon becomes more available, we expect a number of improvements in software tuning as well that will help improve this performance. So Spec CPU is definitely important, but one of the things I wanted to highlight is that we actually really focus on all the applications that people run in networking and in cloud environments. And an example I want to bring up to highlight actually the features that we focus on and why we focus on that are throughput applications such as Nginx. If you look at the life of a request for an Nginx application, the request will come through the NIC, an interrupt will be raised to the system, the TCP IP stack, usually in the kernel, will be invoked such that the request can be taken from its envelope. Then Nginx will look at the request and perhaps will go and ask the file system to grab a file. At that point, the data will come back to Nginx, will be put back in a TCP IP envelope and send it back to the NIC. Nginx can be used in these configurations as a web server, but this is also a very common application for reverse proxy and API gateway, and it's a very, very popular application. So if we look at what matters for applications like this, first of all, we need to be able to move a lot of memory really, really quickly. So again, that's where the caches and the low latency interconnect really matter. Then, as you see actually in the timeline of a request coming in and out, we have to context switch very, very frequently, oftentimes between user and kernel space. Finally, we need to be able to really quickly bring up the front end of the CPU up to speed whenever there is either branchy code or context switches. So how the front end actually performs really, really matters for applications like this. Nginx is definitely an important application, but it's just an example, really. Applications such as memcached, HHVM, and others that are very, very commonly used nowadays have very, very similar behaviors. So what we're going to see is that some of the improvements we made here really apply for a large array of applications. So what are some of the optimizations we did, actually, with these kind of applications in mind? First of all, we really increased our cache sizes. We now have 64 kilobyte instruction and data cache at the L1 level. As I said, the parallel 2 can be tuned between 0.5 meg and 1 meg. And the system level cache can be up to 128 megabytes of capacity organized in 64 banks. The branch prediction capability have also been increased substantially. We now have a 6 kilo entry branch target buffer, a 8 kilo entry by model branch predictor, and a 5 kilo entries history base predictor as well. Additionally, we added a high-capacity hybrid indirect branch predictor as well. The TLBs have been also increased substantially. We now have 48 entries for the instruction TLB, as well as for the data TLB. And we added second-level TLB with 1,280 entries. This second-level TLB also has the capacity of aggregated pages that are right next to each other in such a way the software can actually see a lot more capacity when memory patterns actually allow you to exploit it. Additionally, we really focused on having a low latency, high bandwidth context switch between different execution levels. So hypervisor to guest OS and OS to user space. So what are some of the results actually that we see in the field from these improvements? Well, on the memory side of things, again, we now actually allow cache stashing, so the capabilities for devices to place data directly into the L2 and L3 that was not previously available in A72. We doubled our bandwidth for memcopy, and our caches are up to 4 times larger than on Cortex A72, and up to 66 faster in terms of access time and number of cycles. Context switching, we measured that we're about 2.5 times faster compared to A72. And for workloads such as Nginx, we measured really good improvements on all the metrics on the front end. So branch miss predictions, error caches, and TLB misses have been reduced significantly. As a result, if we compare versus Cortex A72-based systems, we see an improvement of at least 2.5 times on Nginx. This is actually configuring web server as a web server application. So we're very, very pleased about it. Another workload that really matters for cloud users are actually all the applications running in runtime environments, such as Java, CLR, or Python. And what are some of the things that really matter for these kind of workloads? Well, first of all, everything, or almost everything, I should say, in these kind of languages is an object. And the machine really has to be able to allocate, initialize, possibly prefetch, and garbage collect these objects very, very quickly. Also, if you characterize some of these applications, you will see that the code footprint for some of these applications is very, very big. And this is actually because the jitter hopefully actually puts a lot of pressure on caches, TLBs, and in general on the front end of the core. And finally, garbage collection actually comes out again here. I mentioned as part of the object management, but garbage collection is really, really critical whenever you're trying to reach some service level agreement requirements for your applications. And what you want to do in that case is being able to perform operations such as stop the word and restart the word very, very quickly. So you want to be able to synchronize all the cores in the system and between each other very quickly. Okay, so what are some of the optimizations that we put into N1 to optimize for this kind of workloads? Well, we focused a lot, as I said, on the memory hierarchy and on the caches. And what we wanted to do is extract as much memory level parallelism as possible. This is actually both in the front end, thanks to a predict direct fetch front end, as well as by increasing the queues in the back end. We now support up to 46 outstanding system transactions, 32 outstanding non-prefetch transactions, 68 in-flight loads, and 72 in-flight stores per core. We now support both near and far arm atomic instructions, and really we focused on optimizing the cores with the cache coherent mesh such that the whole system can achieve high bandwidth, low latency, and really scale well with a high core count. Again, I mentioned it already, but it's worth actually to bring this up again. Neoverse N1 is the first core that has a fully coherent iCache. That's a 64 kilobyte iCache. And what we found is that having a hardware coherent cache really removes some of the bottlenecks that we saw in the past for core count scaling. So as we look at systems that have 64 or 128 cores, this actually helps a fair amount with workloads that have to move a lot of memory. For instance, actually things such as virtual machine bring up and tear down was accelerated actually greatly thanks to this feature. The L1, as I said, they're fairly large, 64 kilobytes per core, and the load to use is very, very small. It's only 4 cycles. The private per core L2, as I mentioned, can go all the way up to 1 megabyte, and the load to use cycle count is between 9 and 11 cycles, depending on your configuration. Again, we did focus on reducing latency and bandwidth available to the single cores. So one of the capabilities we enable with our machine is to connect directly into the mesh. In this way, the core can really achieve actually maximum throughput for applications that require it. In a system configured with 64 cores and a 32 bank 64 megabyte SLC, we measure about 22 nanoseconds of load to use when actually the cores were trying to address the L3. And what are some of the improvements that we achieved actually thanks to all these features? In terms of object management, the machine is much, much faster in allocating, initializing, and copying memory. One of the smarts actually put in the machine was also the capability for the low store queue to automatically elide barriers that the software programmers sometimes put actually in ARM code, for instance, to match the ARM relaxed memory ordering model with the Java or CLR memory ordering model. We were spending a lot of time in those kind of operations in past machines, and the microarchitects really focused on making sure that those instructions are not even executed if they're not needed. At least they don't take any time if they're not needed. In terms of instruction footprint, when we look at workloads such as latest revision of the Java-based benchmark in throughput, we see, again, the front end behaves very, very well, reduction of about 40% in the iCache miss rate and the branch mispredicts. The L2 accesses are reduced by 2.25 times. So the caches are not just larger, but they also work a lot better. And we're very pleased to see that. And as I mentioned, the fully hardware coherent iCache really accelerates some of the workloads that are commonly used in cloud environments. So we measure that bringing up a virtual machine can take actually takes actually up to 20 times faster on N1 versus Cortex-A72. In terms of garbage collection, as I said, one of the things that really matters is how quickly you can synchronize all the cores. We measure a lock-in throughput and latency, which was improved by 2 times, thanks to the implementation of the new ARM atomic instructions into this core. When we look at comparing versus A72 on, again, a Java-based benchmark set up in throughput configuration, we see an improvement of at least 70%. And these are actually measurements from the silicon. So these systems are really, really good when you put them actually in a high core count configurations, such as the one I mentioned earlier. So again, for a 64-core system, we estimate that the overall TDP for SoC will be about 105 watts, and you should get at least estimated 190 score for Spec in the rate 2017. However, what these cores do is really allow silicon partners to achieve a lot of other design points, thanks actually to their high performance and power efficiency. So for instance, if you're looking for a small edge device or for instance, a smart NIC, you could actually envision to embed 8 and 1 cores in, for instance, a 2-tile configuration. And what we estimate is that a system like that would consume less than 25 watts overall, with less than 10 watts for the total CPU budget. And a system like this, could easily achieve 20 of estimated spec in the rate 2017 or more. Some of the measurements we did in the lab with early silicon showed also that a single Neoverse N1 core can easily push more than 10 gigabits per second of traffic on workloads such as DPDK L3 forwarding. In conclusion, we believe Neoverse N1 offers comparable or better performance to many of the popular cloud instances available and that are going to be rolling out in the next few months. But we can do that at a fraction of the power and the silicon area. So we really think we have a very good TCO story for our partners. Another thing we want to do with this platform is really to show our commitment to our new market, so networking, server, cloud, and edge devices. And really, this is just the beginning. As I said, partners have a lot of opportunities to improve way above and beyond some of the initial estimates and data we are collecting. A lot of software work still has to go into the systems. And really, this is one first step for us to deliver on a multi-generational roadmap that can really fulfill our vision of connecting 1 trillion devices to the internet by 2035. Thank you very much. This concludes my talk. Be happy to take any questions.
Questions? I'm sure Bill Rash has a question for everyone. No.
Bill Rash, Intel. You mentioned a cache stashing feature, and I'm curious if that feature is available to a PCI Express device, and then how does that device sort of signal what data elements need to be stashed or not?
That's a great question. Yes, the cache stashing feature is available to PCI devices, and that will be configured actually in software. So the applications and the OS will be able to program that into, for instance, the page tables on what needs to be done.
Okay, so do you rely on any specific hardware features on the PCI Express bus to do that?
I don't believe we do, but I'm happy to follow up with you on that.
Okay, well, thank you. Mm-hmm.
Thank you.
Andy Glue, Sci5. When are memory barriers unnecessary?
When are they unnecessary?
When can you elide them or make them zero cost?
Oh, that's a very good question. So you're talking about instructions such as DMB and all those? For instance, when you have multiple loads and stores to...
all cacheable? All fast cacheable?
Yeah, exactly.
Okay. Do you allow load-to-load reordering, and can you allow from a single processor or thread, and do you elide DMBs when you've done load-to-load reordering? In other words, can you do load speculation across the DMB?
I believe you could. Cool. What I can do is put you in touch actually with the microarchitect that work on that. Unfortunately, couldn't be here to present with me.
I can guess what you've done.
Okay.
Hi, Jeff Smith, Citadel. I had a question about acceleration of other features I guess a lot of your clients are looking for. So you have, even on die C6, but have you looked at, higher throughput Ethernet max, for example, on die? So if you want to have more throughput with less overhead, having some sort of Ethernet acceleration function and kernel bypass for processing for network-focused applications?
Yeah, that's a great question. So our partners do a lot of smart things actually to accelerate the integration of acceleration IPs with our general purpose compute. So I haven't personally looked at that, but I know actually there are a lot of solutions that actually do rely on our coherent fabric and being able to directly attach through AMBA-CHI actually to the coherent fabric. So partners do that, and they do actually see big improvements when they do it.
Okay. If I could squeeze more question in, a question about the actual network on chip, I guess routing algorithm, if you can talk about that, and also the cache coherency directory structure, if it's co-located with the slices of cache or with memory controllers.
That's a little bit actually out of my scope. So I know the routing for the transaction is XY. Okay. And I believe the cache, the home nodes are in the cache slices. But I can follow up with you if you're interested in more details.
Thank you.
Thank you. Let's thank the speaker again.
Thank you.
So our last but not the least, the last talk of the session is from the company that needs no introduction, IBM, the next generation power processor. And Scott and Jeff and Scott will be the two speakers again for this talk. Jeff received his BS, bachelor's, master's, and PhD from UT Austin. He started at IBM Austin with Power 4 and been doing Power since then, and pretty much done all kinds of stuff. The best way to guess how much Jeff knows is he has mind-boggling 200 patents. Okay, and Scott Wilsberg is a design engineer in IBM's VLSI design group, and he got his bachelor's from Iowa State University, Ames, Iowa, and he has subsequently worked on IBM's microprocessor division for various units of IBM power processor, and most recent, and he has 22 patents also. He's been involved with IBM Power 9 advanced IO features. So without further ado, let's start with Jeff and.
Go through a bit of our kind of strategy as to what we're doing with power. Introducing Scott, we'll go into the detailed description of our latest next generation processor that we'll be announcing. Here's a little bit of the roadmap. There was a request to talk a little bit about how this compared to what we talked about last year and what we are doing going forward. So Power has started this concept back in Power 8 of producing families of processors to address our different markets. And with families of processors, we have chips we do up front in the family generation, and then ones we do later in the family generation. The motivation for these is when we start on something like Power 8, we said we need to address both our enterprise large-scale servers as well as scale-out spaces. And then we had something called NVLink, which produced kind of a third Power 8 family member. We're doing something very similar with Power 9. We initially started off with two different versions of the chip optimized for, one of them optimized for 2 socket boxes, the other optimized for up to 16 sockets. And then what we have here today is a new member to the Power 9 family put in to address a new technical advancement that we wanted to accomplish before Power 10 came along. And so specifically, what we've done is we have new memory technology and new accelerator technology that we wanted to be able to deploy quickly in 2020 to enable us to essentially get access to these new acceleration and memory devices. So that's going to be the primary focus of today. Just to mention roadmap-wise, for 2021, we have our Power 10 processor, which will not only upgrade the memory and accelerator technology that we'll be talking about today, but also a new core and overall microprocessor technology, or transistor technology. That's what we use to delineate different levels in Power 8, 9, or 10, is when we have a new transistor, then we come up with, then we increment the name. Otherwise, we call it within the same family. So what does this mean, though? We view what one might call heterogeneous systems. I kind of like the term composable systems as what IBM needs to have access to build our leadership systems going forward. And so what this means is we really need to focus on building diverse acceleration devices and diverse memory devices beyond just CPUs. Back when I started on Power 4, our goal was, we had to have memory. We had to have a certain amount of memory capacity, but the focus of that project was, the project was called Gigaprocessor. We were trying to get a CPU to run at a gigahertz. And we got a 1.3 gigahertz processor. The next generation, we got 2.5. We got all the way up to 5 gigahertz, focused on new technology and new CPUs. But one will notice that we've actually dropped below 5, and now we're in the 4 gigahertz. So we can't focus on CPUs anymore. We need to focus on heterogeneous systems. We also need to be able to quickly deploy different types of heterogeneous systems. So that's our focus. Let's kind of get going a little further here. So what do we have with regards to acceleration on Power 9? Our goal here, to a large degree, is to minimize the different types of SerDes we have off of our processor. So we're trying to remove having to put a DDR PHY, an PCIe PHY, an SMP PHY, an accelerator PHY. We want to consolidate those down to a smaller number of designs. And where we're at with this newest version of Power 9 is we have 2 SerDes technologies. We have PCIe, which we need to maintain to get access to the large PCIe ecosystem. So we have Gen 4 PCIe running at 25 gig. Everything else, though, off the chip is off of our more efficient 25 gig signaling technology. Now, what makes it more efficient is that it's been optimized to only run at essentially 25 gig, a limited frequency range off of that SerDes. And because of that, our SerDes expert is able to make something that's significantly more power and area efficient than you can with PCIe, that has to be able to manage to run across a broader range of frequencies, because you can plug a Gen 1 PCIe card into a PCIe device, and that is a fairly reasonable compromise in efficiency. So what we do is we want to then take all of our signals coming off the chip that are 25 gig and then be able to deploy composable systems where in some cases we'll plug in an NVIDIA GPU and call it NVLink and flip a switch and make it run NVLink. Other cases we can plug in FPGA accelerators, run an OpenCAPI protocol. We can also take that same SerDes and run OMI, which is our new SerDes-based memory interface, open interface. The OMI stands for Open Memory Interface, which is a JEDEC standard, SerDes-based, so differential signaling memory attached technology. So essentially what you have here is off of PCIe, we can do traditional PCIe. We also have a coherent extension to PCIe called CAPI. And then across the 25 gig signaling, we can run NVIDIA GPU and NVLink. We can run our OpenCAPI technology, which is our open accelerator coherent attached strategy. And then we can also use those same SerDes to do our DRAM to give us a significant boost. There are on-chip accelerators as well. The most probably exciting one or interesting one is our GZIP accelerator. We've had a fair bit of usages with an on-chip GZIP accelerator for things like accelerating storage and network. So for some of our supercomputer deployments specifically, they had very high writes to storage. And if you compress it with a hardware engine before you write the storage, there's a pretty significant effective bandwidth and capacity growth in your storage. So that GZIP accelerator offers fairly dramatic compression rates at essentially no CPU overhead. So what do we get by building these composable systems? IBM has delivered the 2 fastest supercomputers on the list currently, and these were partnerships taking Power 9, the previous version Power 9, with NVIDIA GPUs and Mellanox networking. So IBM, being a system company, is interested in being able to deploy these high capability systems, and we're okay doing it as an open collaboration, or we feel like we need to do it as an open collaboration to be able to create these large systems. So let's spend a little bit of time talking about OpenCAPI, as we see this as being very important towards these new accelerated systems. And I see a lot of people in the audience here are building accelerators, and so I want to enable people who want to build accelerators to do so quickly and with high performance, not having to have the latency and some of the overheads associated with PCIe, for example, at least today's PCIe. So what type of devices are we talking about? We want to enable accelerators to do caching of host memory. We want to enable the host CPUs to cache accelerator memory. Why would we want to do that? For accelerators, also for networking devices. We see some use cases where people want to offload collectives or accumulates in the network. And the way you want to do that isn't through complex software to go ahead and assign blocks of region to pin memories to accelerators. We want to just be able to have the software be able to take any memory location and cache it in the network, where it can update those things, atomics, things like that, and then have it all work from a coherence perspective. The other side of things is memory is becoming much more diverse. You've got traditional DDR memory, but you also have emerging persistent memory and things like that. We want to be able to attach those devices and a common interface while still achieving low latency when we plug in traditional DRAM. And this is something that we've been working on at IBM for quite a few generations. We started doing, the first project I worked on, Power 4, had a differential memory buffer. Right? We've had differential memory buffers in power systems going back prior to that. Essentially, the last 25 years, we've used differential memory buffers. The one exception to that, actually, is the Power 9 product that has direct attached memory. But because of this long experience of building differential buffers in various form factors, we have quite a few sort of, I won't call secret sauce technologies, previously sort of secret sauce technologies, but now these technologies we developed are in our open standard. And so we very much want to encourage other vendors to participate in this open memory standard. So let's talk a little bit about accelerators, though. And this was a key point that, as we've been investigating other standards in the kind of accelerator attached space, is the symmetry or asymmetry of the design. So if one is going to build a host silicon machine, and we want to be able to quickly develop accelerators, that pushes you down a design point where that interface is not symmetrical. You want to be able to build a lot of work into the host to quickly develop your accelerator technologies. And so why does it want to be asymmetrical? Typically, a symmetrical protocol would be tied to a specific cache coherence protocol in states, a fairly complicated one. You want to hide all those things from the accelerator, so the accelerator doesn't want to have to understand, oh, this is the x86 page table translation structure, or this is the ARM page table structure. You want to avoid having the accelerator know about the page table organization. Design schedule, this is fairly obvious. Host CPUs take quite a while to build. Part of the reason they take a long time to build is they have to implement the entirety of the instruction set architecture. They have to make sure they have backward compatibility for any code that's been run before. This is maybe obvious to the audience, but CPUs are typically built with more writs, or we call them, or tape outs, I should say, than an accelerator. Accelerators are made with less passes because you can't run user code on a GPU, right? So if there's some late breaking bug associated with some instruction, obscure instruction in the GPU, that gets removed. With a CPU, you got to run everything all the time, and so it takes longer to build these things to get them perfect. So what we want to do is enable people to build accelerators where they don't have to worry about obscure address translation scenarios. They don't want to have to worry about handling interrupts from I/O unless they want to. So that forces us to try and do as much work for the accelerator as possible on the host to make the accelerator simple. A design corner as well, these are some optimizations in OpenCAPI where we do things in the host silicon that are inherently going to be faster than in a SoC ASIC sort of turn the crank process. This is really tied to formatting of data as it arrives. Trust is another important feature here. It's not that we don't trust people building ASICs, but there's more likelihood that they would have an error due to the shorter design schedule. And so we build protection mechanisms in OpenCAPI that prevent an accelerator from, say, crashing the whole system due to a cache coherence flaw. We've simplified our cache coherence protocol that the accelerator sees to prevent rare race conditions, right? Having been building systems for 25 years, you really don't want to have some rare coherence condition occur when somebody plugs an accelerator into their box in the field, right? You need to make sure that everything you do with the accelerator is provably correct, and they cannot introduce weird coherence bugs, and making the cache coherence simplified enables that. And so we're strong proponents of having an asymmetric protocol in our coherence. We've had this in OpenCAPI for several years now. We had this in CAPI prior to that. Really going back to Power 8 when we first introduced CAPI is how long we've been pushing this design philosophy. Some of the things that are also interesting, and this is where things are different between PCIe and OpenCAPI specifically, is that to achieve low latency and optimized data flow, we have aligned all data packets with the deserialized interface width. So PCIe, things can start on arbitrary boundaries. This forces rotators and things like that in the receive silicon. So part of that optimization around simplifying the host silicon is we always align data packets on the deserialized version of the interface. So essentially, your accelerator device sees a 64-byte wide packet that's always aligned, that always has the same alignment of things. That helps on latency, though, because now you don't need to go and search for the start of the next packet. You can actually make assumptions about when a packet arrives. Oh, I know the command is going to be in these specific bits. And so you can actually start processing the command before you've even checked the CRC, because you know if that interface went from a 0 to an 8, then that means I see a read command. Okay, I'm going to go start working on that read command. And if there happens to be a rare CRC error, you just flush the device. So this enabled us to build, kind of a very optimized, tight interface. Now, part of the problem with doing an interface like this, or I should say the compromise, is that it's very difficult to make a switch that can do coherence and that can do this sort of split transaction read-write feature. There's really a list of reasons why switches are hard with coherence. One is the number of virtual channels one requires to implement coherence protocols and I/O protocols and memory protocols on the same device. You end up with a fairly significant number of virtual channels. So if you're going to be able to switch with all these virtual channels, you got to have buffers for everything, and that adds quite a bit of complexity to the switch. Beyond that, and this is true with every of the competing protocols I've seen, or all the different protocols, is you have to have dedicated buffers for coherence between the host and the coherent device. So if I'm going to do a cache eviction, I have to have a home for that cache eviction to land in, otherwise I deadlock. And so if I've got 8, the coherent devices on a switch, not only do I need to put in 8 sets of virtual channels for all of them, but I also need to have dedicated resources in the host for every device I attach to it. So I mean, these are the types of problems that make, the reason we don't support switching with OpenCAPI, essentially. Because doing coherence over switches is really has a dramatic number of sort of n-squared types of problems. So that is a bit of a design choice compromise, is that it's really a host to an accelerator tight relationship. So let's talk a little bit about memory. This is pretty interesting, really, and we're very excited about sharing our memory technology with other people in the audience here. You'll see Scott's charts talk about how we have 6x the chip area cost for memory, or I should say 1/6 the cost to put on our OMI memory interface instead of DDR. So if you're an ASIC person out there and you want to have memory on your device, what you need to do today is you got to go obtain a DDR PHY, which is in addition to whatever PHYs, PCIe PHY or other PHYs you want to have on your device. And those DDR PHYs, the amount of area they take for a given amount of unit bandwidth is quite poor. Even at 3.2 gig DDR memory, you're still running at 1/8 the frequency which you can run at on a more traditional Ethernet differential PHY. And so because of this, while we took our big processor and stuck a whole bunch of these things, 128 lanes of it around our chip, if you're a smaller chip, you could take 16 lanes of this. And 16 lanes of this is 1/6 the size of 2 DDR ports. And so if you're trying to get more bandwidth into a small ASIC, this is really a very good solution. The other thing that is important about the way we do differential buffer attach, which is different than like how FBDIM was done back in the day, is we are technology agnostic. We started this in Power 8, where it's a tagged interface. The memory scheduler is on the buffer. So the request from the processor just says, go do a read. go to a write. It knows nothing about the particular electrical standards or ordering standards or bank conflicts of the media, and therefore one can decouple what type of media it is. So if you want to put GDDR memory behind a buffer, the host doesn't care, nothing changes. This is different than previous protocols. We started this in Power 8, though in Power 8 it was a proprietary protocol, and so we couldn't get a whole bunch of vendors to go off and build media for us. So what we did with the OMI standard, which is what we're talking about here, is we made it lighter weight so you can build smaller memory devices, and we also made it open. So that's what we have here. So what we envision is we want to be able to address a broad set of memory devices. Low capacity, high bandwidth, those might be based on GDDR or something more custom. What we have immediately is a DDR4 device, which is essentially a buffer and a DDR4 DIMM. But we see the ability to build higher availability, larger form factor devices. Mixed devices could be tiered memory, which combines DRAM and a second tier of persistent store. It could be all persistent store. But we see a broad range of different things we can build here. What does that look like is, this is trying to compare the options. And the options here, if you look at DDR4 today, you build a piece of host silicon, you build it to support DDR4. You can range capacities by going, registered DIMMs, lower cost. You can do load-reduced DIMMs that get you to higher capacities. But it's going to be very challenging to plug a DDR5 device or a GDDR device or all these different types of devices into the same chip, let alone the same system. With the OpenCAPI memory, the OMI memory, based around some OpenCAPI SerDes technology, we could take DDR4, plug it in, DDR5, GDDR, arbitrary devices, all into the exact same system in the same connector, right? And this enables us to not have to go build a new version. One of the questions associated with AMD is, okay, if you wanted to support DDR5, could you rebuild the hub chip? Sure, you could, but that's a big chip you have to spin and a new system deployment. With this type of memory technology, when DDR5 comes out or whenever it becomes economically viable, you take your existing systems, you pull out the DDR4 DIMMs, you plug in the DDR5 DIMM, right? So this decouples memory technology from host silicon development. The other interesting technology out there is HBM. HBM offers higher bandwidth, right? The highest bandwidth we think we can do with OMI in the immediate future is 650 gigabytes per second per socket. Pretty impressive bandwidth, but still not nearly as high as what we see with HBM memory integrated on the same module, right? That's in the terabytes per second of bandwidth. That said, you have to be very specific. It's built into the module. You don't have a wide range of capacities, right? So it makes sense for some high bandwidth situations, but it doesn't offer us the flexibility we get with this sort of one sitting in the middle. So let's go ahead and introduce Scott. He's going to talk about the chip in detail. Thanks.
Hi, my name is Scott Willenborg. I was the chief engineer for IBM's Advanced I/O Power 9 processor. So I'm here to talk a little bit about the chip that we actually built. You can see the die photo here. Left side shows some of the features that are common with our Power 9 processor. Same 14 nanometer technology, 17 levels of metal. Some of the signaling technologies are the same. But on the right shows sort of the advances that we made leveraging some of the things that Jeff was talking about. So specifically, we've got an open memory interface that's using the emerging JEDEC standard to have 16 channels by 8 running at 25 gig transfers per second, and as Jeff mentioned, 650 gigabytes per second peak bandwidth. Technology agnostic, so our first implementation we're going to be using, what we're going to offer with microchip DDR4 memory buffer, and we'll be able to change that to DDR5 or whatever as the memory technologies advance. The second main area that we changed on the advanced I/O chip was we added support for NVIDIA's next generation NVLink. So we'll be able to attach our next generation GPUs onto this chip as well. And then the third area was our support for OpenCAPI. We added support for 4.0. Power 9 had support for 3.0 version of the architecture, and we've added support for version 4.0. And I'll go into a couple specifics on that in a later chart. And then, of course, we've still got the things that Power 9 had, such as our OpenCAPI 2.0 or our CAPI 2.0 and our PCI Gen 4. So this shows a potential system offering that we have with this new chip. You can see the 4 NVIDIA next generation GPUs talking to each other to do your acceleration. We got the OMI memory on the top and the bottom, as well as OpenCAPI interconnects, and then your PCI Gen 4 as well. So this is sort of a 2-socket replacement. It shows a 2-socket here. The chip can actually scale up to a 16-socket. This 2-socket is sort of showing the equivalent of what we used to build the supercomputer picture that Jeff showed earlier. That was built on a series of 2-socket systems, and this is sort of showing what we could do with the new chip as well. So a little bit on OpenCAPI 4. I'm not going to go into all the boxes here. There's a lot of data here, but I just wanted to show that we've been doing CAPI and OpenCAPI for a lot of generations now. I think this is our 4th or 5th generation. You can see that when we went to OpenCAPI 3 on Power 9, it became an OpenCAPI architecture where you can attach to any host. Doesn't have to be just Power. It could be any particular host. And with that, we've got support for 64, 128, and 256 byte cache lines. The things that are most significantly different between going from OpenCAPI 3 on Power 9 and OpenCAPI 4 with the advanced I/O chip are we've added the ability to send short messages, 128 push messages for low latency. We've also added posted write support, so you can stream writes up to memory and kind of fire and forget them. And then we've also added the ability to have a virtual address cache. So your accelerator can actually cache system memory and use it directly right there and get the latency advantage of doing so, and the host manages the higher level cache coherency protocols. So some of the different connectivities that we have on the Power 9 family, if you will. The left picture shows a Power 9 scale out where we had our direct attached DDR memory, and we had 24 lanes of accelerator and some local interconnect for hooking sockets together. In the middle, you've got our scale up, which Jeff talked about last year at Hot Chips here. And there we used our Centaur memory buffer, the DMI buffered memory. And that has, it's a denser footprint from a memory perspective, so it allows you to get up to 3x the bandwidth per millimeter. And now when we go to our Power 9 Advanced I/O, we actually go to the open memory interface that I mentioned, which is, again, the open JEDEC standard. And that gets you another 2x bump from that from a millimeter perspective. So we've got up to 16 channels, and we've also got up to 48 lanes of acceleration of either NVLink or OpenCAPI. So this shows the DIMM comparisons, just kind of pictures, kind of show different sizes, and you can see on the top there a larger Centaur DIMM, kind of more your standard DDR, and then on the right side we've got our actual DIMM that we have with a microchip buffer in the center, showing kind of the small form factor there with low cost. It's got it's got enterprise reliability built in with chip kill and ECC. And there's been a big focus on the low latency, which I'll touch on. So I mentioned that with the OMI, it's signaling at 25.6, so that we can attach 3200 megahertz DDR. And when we started the design, we had a goal of having less than 5 nanosecond latency adder compared to an LR DIMM design. And for reference, our IBM Centaur design had about a 10 nanosecond difference. So Microchip's SMC 1000 is the chip that they've developed that we've got in the lab right now. And so how did we do, right? This shows a little bit of the block diagram of the pieces of the parts, and essentially what they've been able to achieve is less than 4 nanoseconds incremental latency over a traditional DDR controller with LR DIMM. So real close to our 5 nanosecond target, and a small delta latency add compared to what we, for the additional bandwidth that we get. Some of the ways they've been able to do this is, for one, they've gotten rid of all the asynchronous interfaces, so you don't pay an asynchronous penalty. And then for data coming from the host down to the DRAM, they do some early address pre-decode and to allow some address prediction on what they're going to need to fire up for the address lines. and then coming back from data coming from the DRAMs up to the host, they bypass ECC, correct and detect. And then if there does happen to be a rare ECC error, we go ahead and poison the CRC so that the host sees that it's bad, and they go ahead and replay that, and by that time, the data's been corrected. Okay. So that sort of concludes kind of the presentation. I'll ask Jeff to come back out for some questions. But we, like I said, we've had three main goals with this chip, and that was adding the OMI memory, the new NVLink protocol, and our OpenCAPI 4.0. Thank you.
Time for some questions.
Let's see what the question is.
Hi, Jeff Smith, Citadel. One of the slides qualified the characteristics of the memory channels being energy efficient. Is there, energy per bit, ballpark figure you guys have for this versus just, vanilla DDR DIMM?
I don't have those exact numbers. Keep in mind that we shifted power from the DDR5, which is actually a fairly power-hungry device, off of the host silicon onto the memory DIMM, which helps with overall, cooling conditions. It also should be noted that the 8-lane memory device automatically moves to 2 lanes or 4 lanes based on usage.
Okay.
And so when it's at 2 lanes, the power of it's quite low. I don't know the exact number on the top of my head. I don't want to tell you the wrong number, but it does dynamically shift the lane width based around utilization of the link.
Thank you very much.
It's lower power on the host silicon than it would be if all those DDR5s were on the host silicon.
And how big is any extra buffering on the Centaur buffer itself? Or how much extra SRAM or whatnot is in that, or EDRAM?
You're asking on the memory buffer chip, how much?
On the buffer chip on the modules, yes. Is there actually extra cache there? Or?
So the new one does not have a cache. It's strictly just write buffering.
Oh. Correct.
Yeah, and that's probably worth mentioning. The Centaur chip had a 16 megabyte cache and 4 DDR channels. This is a much more slimmed down device, which lets us put it on that, 1U short DIMM, which is really 1 channel, just write buffering, no caching.
Thank you very much.
Hi, Alan Cantle, Molex. So this looks very much like the recently announced CXL from Intel, yet it's in production and you can buy the memories today. Why would we wait for CXL?
Wow, Alan, that's a very interesting question. I do think it's, I'm viewing CXL more as being something that's on the accelerator side, to be frank. And this is something we have today, which is the OpenCAPI acceleration devices, which is ahead of the competition. Certainly all the thoughts we have been around for quite some time, so we're leading here. I'll be surprised if other buffered memory solutions achieve the latencies that we've done with this. There was a press announcement recently about another standard that had the ability to attach memory, and the latencies were dramatically higher.
The CXL does have a separate memory as well as the accelerator.
Correct.
One would hope they would adopt OMI.
Yes, I've seen that it's in the brochure, but I'll be surprised if it has the handful of nanoseconds latency penalty that we built with this device.
Okay, let's thank the speaker. There are no more questions.